Okay, guys, we're going to get started. So our last talk for today is Exploiting Modern Microarchitectures by Jon Masters. So please help me welcome him with a warm round of applause.
Well, thank you very much. We'll see if you're still clapping at the end. So my name is Jon Masters. I'm a computer architect with Red Hat. Some of you know me from the Linux kernel podcast and from some work I do with the ARM architecture. But I'm actually here today to talk about something completely different. Put your hand up if you have never heard the words Meltdown or Spectre. Okay. So I'm here today to talk a bit about a little project that we were running inside Red Hat. So I was running a mitigation team for the past few months dealing with this event, and a bunch of us didn't really get a holiday as a result. And so over that time, we learned a lot about these particular exploits and also had a time to reflect on these new classes of attack and what they mean. And so the purpose today is to both introduce these two exploits that you've heard in the news, or the three variations of them, but also to walk you through some concepts in computer architecture that they exploit, have some time to think about where we're going as an industry, and then we'll take questions toward the end. Now, I did a preview version of this talk a few days ago at Stanford over in California, and it took 2.5 hours to get through the slides. Now, the good news is that I have only 45 minutes here, and I've added 5 slides since. So what you're going to see is, at various points, me skipping over slides that contain explanation for diagrams that I've showed you, right? The idea is that if you want the long-form version, in particular if English is not your first language, or this is the first time you've seen a concept, you can go and read the long-form explanation, and you can download the slides right now. If you follow @JonMasters, that Twitter handle right there, you'll see a link, and we're going to do a load stress test on people.redhat.com. We're going to see how well it stands, everyone trying to download these slides at the same time. So feel free to pull them down and look ahead and speculate about what's coming in the future. Thank you. Okay, so, and I would like just to ask a couple of quick questions. So, hands up if you have studied or looked at computer architecture in the past. Okay, good. So the first half of this is going to go really quickly. Hands up if you have read the paper or papers relating to the exploits I'm talking about today. It's a good show of hands. Hands up if you think you understood it. Okay, that's still a good set of hands there. And hands up if this is all fairly new to you and you would really benefit from me walking through it in some level of detail. Okay, good. So about 50% of you think you know everything I'm going to say, and 50% of you are not sure. So that's a good mix. So today's class is going to cover, I did take this from the deck I showed at Stanford, so it was a lecture at that time. Today I'm going to cover the difference between architecture and microarchitecture, some variations of microarchitecture, so what that means in the real world. I'm going to talk about caches and virtual memory and branch predictors, which are some of the pieces that you need to exploit to make these kinds of attacks successful. I'll talk about side channel analysis, which is an interesting topic in itself. And then I'll look at the actual vulnerabilities that you've seen, the mitigations we have for them, and then finally some related research into hardware exploits that maybe you have not seen before. So, architecture versus microarchitecture. For those of you who are at the RISC-V sessions, you probably saw similar content already. But when we talk about computers, we have this concept of architecture, and an architecture describes, at an abstract level, how a machine operates and behaves. So it describes the kinds of primitive instruction that the machine actually executes, the ones and zeros it executes. So when I see this particular sequence, do this, right? Describes how to load and store values from memory. It describes the registers, the machine state that I have. And it describes various modes of operation, privileged and unprivileged modes of operation we'll talk a bit more about in a moment. And then there's more detail as well. It describes memory models and other things that you might find very interesting if you pursue architecture. We also have some software concepts we care about. So if we are Linux programmers or BSD programmers, we care about running programs known as processes or tasks when they're running. And we care about the fact that they execute at different privilege levels, right? So applications are less privileged than the operating system. Applications run in something we call user mode, and we have various abstractions that protect them from corrupting one another and from corrupting the kernel, right? So we have this virtual memory environment we define so that our application sees this nice flat view of memory. It thinks it's the only thing running on the machine, unless we tell it otherwise, and it requests services from the OS kernel when it wants something performed. It doesn't explicitly have knowledge of other programs running on the machine. It can find that out. It could ask the kernel. But as far as it's concerned, it has a view of memory that's all to itself. The OS, on the other hand, has a privileged set of architecture instructions, and it uses these to manage the state, to manage the context of the running programs, and to switch between them. So when you get what's called a hardware interrupt, when you get some event coming in, or otherwise need to switch from one program to another to give the user the illusion that lots of things are running at the same time, that's what the kernel is doing. It's using these interfaces to save and restore the context of programs. Examples of computer architectures. Obviously, I have to mention x86 first, right? I think everyone here knows what x86 is. I could have put RISC-V as the second one. I decided not to. I think you guys have heard of that too. But these are two examples of architecture. So, x86, it's a bit older than the 64-bit ARM architecture. They both have instructions. One of them takes complex instructions. One of them has simpler instructions. They both operate on registers. And they both have a 64-bit memory model. They can both use large amounts of memory and provide that to applications. There's some differences, but at a high level, we can compare the two. Let's talk about microarchitecture. So, a little detour. I'm a very bad graphic designer, right? So, don't ever come to me if you want something pretty. Here's a picture of a chip. And the thing I'm trying to sort of represent here is that a modern processor, as we think of it, is actually, it's not just one little CPU doing something. It's not how we used to think of it years ago. A typical chip in even your laptop or your phone will have many cores. We used to think of these as processors back in the day, but there are many different cores, and each one might be running a process, or several of them together might be running threads in a process. They're all connected together on the chip, and they have these high-performance interconnects. So on here you can see I've got 1, 2, 3, 4, 5, 6, 7, 8 cores, and they have shared access to some of the resources. So there's a memory interface on each side of my chip, and whenever I want to load something from memory into one of my cores to do some processing, it's going to come in through the external memory interface, and it's going to work its way up through levels of cache. We're going to talk more about that in a minute. But just have this picture in your head, and we'll talk a bit more. So programmers think of processors, but they really mean cores. We have these systems formed from many different pieces, and they all have to work together. Microarchitecture refers to an implementation of an architecture, right? So we've defined a high-level x86 or ARM instruction set architecture. We've said this is what an x86 machine has to comply with, and a specific x86 machine might be implemented differently from another one. As long as they can run the same instructions, the implementation can differ. And some example differences can include what we'll talk about in a moment. In-order machines, out-of-order machines. Lots of differences can exist at a microarchitecture level. For example, simpler processors are often described as being in-order machines. And if you're not familiar with computer microarchitecture, this might be how you think of a processor when it's running your code. So when your program is running, every single instruction, every single operation in your program, what it will do is one after the other. It will fetch the instruction, it will decode, figure out what it does, and it will execute that instruction. And it will rinse and repeat that one after the other. This kind of example is kind of your classic RISC machine. If you were to take a simple RISC-V machine, for example, it probably will start out, there are some more performant implementations, but it will probably start out as a simple in-order machine. And what we might do is we might add some features like pipelining. So instead of having, I mentioned the different stages there before, we might overlap them a bit. We might say, I fetch one instruction, I start with figuring out what it does, and I'm already fetching the next one, and I get a little bit of parallelism here. You can see here, I might have 5 instructions working their way through the machine at different stages, right? That's called pipelining. That's when I split out how my machine executes instructions into smaller steps. It still does them one after the other, though. In-order machines are easier to implement, and they're much more efficient in some ways from a power perspective, right? So I'm not going to get very high performance, but I'm going to need potentially less power. So that's why you tend to get those in little widgets. And they'll also use less area. They physically are smaller to build. But they're susceptible to things like pipeline stalls. So if I'm working my way through the different stages of running instructions, and I'm trying to load something from memory, I might have to stall my machine while I wait for some data to become available. They've got a limited capacity to hide the latency of instructions as a result. Now, what I can also have is an out-of-order machine, right? Now, this is very different from what you as a programmer are thinking of. So when you write a program, you think, I do this, and then I do this, and then I do this. But what the industry has done is spent the last few decades working out how to take your program that has a defined sequence of operations and to automatically work out dependencies inside your program. So here's a simple program. I'm going to load 2 values, I'm going to add them together. And here, I'm going to load 2 values and add them together. Those of you who are familiar with assembly language will see that I'm using registers inside my machine. I'm loading register 1, register 2, and I'm storing the result of adding them together in register 3. And here I'm doing the same. Load register 1, load register 2, add them together. But these 2 sections here, they're actually independent. I could renumber these and use different registers. There's no reason that I have to have the same register numbers here that you see above. In a simple machine, it might run through that program and execute it exactly as you see here. In a more complex machine, what it might do is work out, well, actually, these 2 sections are completely independent. And the only thing they share is that they're using the same registers. But I could actually change that. So behind the scenes, what an out-of-order machine will do is it will reorder all of these instructions. It's called dynamic execution. And what it will do is it will say, actually, the moment that these values are available, I can run this instruction. And then what it will do is something called in-order retirement. So you start with your program that does one thing followed by another. You turn it into what looks a bit like a data flow machine. And then you do in-order retirement. So at the end, when you've worked out your results, you keep track of where you are, and you say, okay, I may actually be executing this stuff here before this stuff here, but I'm going to wait, and I'm going to retire only in the sequence the programmer expects. So you as a programmer are not aware of this happening. And then there's some complex machinery that's added for exception handling. So if something erroneous happens during execution, I might have to back up what's happening inside the machine and present it to the programmer in a consistent order and say, well, you had a failure here, and that is actually, I'm presenting it to you in the order it would have happened from your point of view. So this is very complicated. I want you to understand, though, that machines that you have, even on your laptop in front of you right now, may actually be executing programs in a completely different sequence from how they were written or how you imagine that they would work. Out-of-order machines are very common in high-performance microprocessors. The concept was invented by a gentleman called Robert Tomasulo, who unfortunately passed away a couple of years ago. And it would be interesting if he could see kind of the media attention recently and get his insight, right? Because what people have done, I'll talk more about speculation and how that builds on this in a moment, but what people have done is they've said, well, this whole thing doesn't work. Actually, it does. It's working exactly as designed. There just can be some flaws in specific implementations of this. But Tomasulo invented this back I'm keeping an eye on the time because this is going to go long otherwise. He invented this for the mainframe, the 360 Model 91. So quite a long time ago. And then over time, it's worked its way down into computers that you have on your desktop, on your laptop, and in most phones as well. And as I said, instructions are dispatched from an in-order front end, as we call it. They're executed in this out-of-order machine, and then they're retired back in sequence. And the size of the structure I alluded to here dictates how many of these instructions I can have out of order at a single moment. And these can be quite large. So in a contemporary machine, for example, a Skylake processor, a recent x86 implementation from Intel, the Skylake microarchitecture has a reorder buffer that's 224 entries long. So that's quite a few instructions I might be ahead at any one moment. That's a lot of housekeeping they have to do. That's why these things are very, very complicated. You should also know the average one of these processors costs about $1 billion, takes about 4 years, and needs at least 300 people just for the basic design, right? That's why you don't have open source. You have open source out-of-order machines, but one reason we haven't yet seen a Xeon class open source design is frankly the amount of cost that someone has to throw at doing that. It's not to say it won't happen, but it's very, very complicated and very expensive. I'm going to skip. Oh, well, and this last slide here just talks that there are lots of questions you can ask about architecture, right? So I have an architecture specification, for example, x86. I then talk about how I implement that, right? When I'm executing my instructions, do I do them in order? Do I do them out of order? These are all design choices. The machine ultimately runs the same programs, but I have trade-offs. I can make choices based on how complex and how performing I want my machine to be. Examples of implementations of architectures. So here's the Skylake in my laptop. That's why I'm using that example. It's a little bit older. And you can see it's got 224 instructions that it can have in that ROB. And then you've got an IBM Power 8, which also can have 224 instructions, but they call it a global completion table because IBM is different in lots of ways, good ways. And you also see, how many instructions the machine could have in flight. So on an x86 machine, typically it's a couple at a time. On your laptop, it will take these x86 complex instructions and decode them further into these macro and micro ops and all kinds of things you can read more about later. It'll run a few of them at a time. On the really big servers, it might run as many as 8 or 10. It may dispatch 8 to 10 at a time. Okay, now, store that, what I just said. Let's talk about virtual memory. Okay, so I talked about the separation between applications. You have user space, you have user applications running, you have the operating system, And we try to isolate the two for obvious reasons, right? We don't generally want any old application being able to interfere with the operating system. And we have a defined interface between the two. So when an application wants to do something, it uses a system call interface, an API, through which it requests things from the OS. Applications, when they're running, as known as processes, they use system calls. I think I mentioned all of that. Here's an example of a program when it's running. So if I were to, just on my laptop, type this command, cat proc self maps, I could see the view of memory that cat program has, because it's catting its own memory map. And I might see various memory ranges. But I really want to draw your attention to a couple of them. Okay, so every process, every running program, will have a range of memory that represents its own text, its code, and its data, and its stack and some other stuff. And then every process, until recently, we'll come on to why that changed, until recently, would also have this range of memory at the top of its address space, which contained all of the kernel and all of the memory that the kernel has access to. And you might say, well, why is that? Well, we have mechanisms that are supposed to protect the application from being able to see or touch that range of memory. And it means that whenever we want the kernel to do something on our behalf, we can have a very lightweight entry and exit from the kernel. It already has access to all the memory it needs. It's already set up. We just jump into a different execution state that can access that memory. We do something. We go back to the application. So the application shouldn't be able to see any of that memory. We maintain this separation using something called page tables, which take the view of memory the application has, and they translate it into the view that's seen by the hardware. So I'm trying to access, this address, whatever address up here. It's going to go through some page table that tells me where in physical memory that address actually lives. That's an expensive operation, doing that. There are things we call hardware walkers in our chips that actually have to go down through these tables, and they have to work out this translation. That's an expensive operation. So we don't do that every time. What these chips have in them is something called a translation look-aside buffer, actually probably several. And what these do is they store these translations. So if I want to touch a piece of memory, I can actually look up very quickly the last few translations. And again, by keeping kernel memory translations in place, while my application is running, again, I get some performance. Because if I want to go into the kernel to do something, these entries are already populated. They're already present. And so typically what I will do is I'll leave these in place until I switch from one process to another. Then I have to flush this stuff out and switch to another process because its view of memory is different. Okay, I'm going to skip that slide. Skip that one. And, okay. So I'm going to throw caches in here as well. So I've said that you have these ranges of memory your application sees. You translate them before they hit physical memory. Well, you also have a caching hierarchy that sits between your program accessing some memory and the actual RAM chip in your machine. And there are multiple levels of this cache memory, right, with names like level 1, level 2, level 3, level 4, things like that. But basically what they are ways of accessing data that I'm using frequently faster, right? Memory chips in my machine are slow, relatively speaking. The cores inside my chip are much faster. And the laws of physics tell me that I can't have both. I can have big and slow or small and fast. So what I do is I have some memory on my chip. It's a bit faster, or a lot faster, and it caches values I've been using recently. So when I touch a piece of memory, what will actually happen is it will get pulled into the caches. And so for example, I may have a cache entry for a user, a piece of data from a user application. I may at the same time in my cache have a piece of data from my kernel. And again, I've got protections in place that should mean that there's no way of ever accessing a piece of kernel data from my application code. Right? My page tables say that's not accessible. Doesn't matter if it's in the cache. When I try to access it, that's not accessible. I'll probably skip this slide, but this is an optimization, actually, of how modern high-performance caches are implemented that you can read a bit more later on if you're interested. This will tell you, for example, if you ever wondered, why is a level 1 cache 32 kilobytes in every CPU with 4K pages? This will tell you why. You can read it later. Let's keep going. Okay, I'm going to skip how caches work. So let's talk about side channel attacks. So side channel attacks are based on deriving information by exploiting the physical implementation of a machine, right? So we have our instruction set that describes how any x86 machine should operate, for example. Then we have an implementation. The side channel takes advantage of the fact that an implementation might have some vulnerabilities into it. Classical things that we've done in this space have involved electromagnetic emissions, right? Put your hands up if you've heard of Tempest. You guys heard of Tempest, right? The sort of secretive governments, agencies watching your screen from afar, right? That's based on analyzing the emissions coming from your machine, right? There are similar attacks with differential power analysis, so I can monitor how much power a chip is using, and I can infer what it's doing. Another thing that I can do is I can measure how long it takes for certain operations, if different operations take different amounts of time, and if I can actually perceptively measure that. So caches can behave as side channels because they're a shared resource. As you saw from my diagram earlier, whenever I want to use a memory location, it's going to go in through my cache hierarchy, meaning that the cache is shared by everybody. And I can actually measure a difference in the time it takes to access a piece of data based upon whether it's in the cache or not. And in fact, it gets even more scary. You can actually work out what level of the cache it's in. Oh, that just rebooted, so... All right. If you're watching the video stream and it cut out, your video streaming machine just rebooted, but okay. Anyway, so I can measure the amount of I can measure where or if not in the cache based on how long it takes to read a piece of data. In fact, there are even more exciting attacks. On some architectures, like x86, I have a special instruction called CL flush, and I can say, as a programmer, unprivileged, any code can do this, flush this location. Make sure it's not anywhere in the caches. So I can guarantee it's not in the cache. And actually, what I can do is, if I do 2 flushes, I can actually measure whether, when I flushed it, whether it was in the cache to begin with. So I don't even have to load something to measure whether it's in the cache. There's some really exciting attacks I can do. Here's an example. So I have these interfaces on most architectures. I have a way of measuring time. On x86, it's called RDTSC, Read Timestamp Counter. I can read the current timestamp counter, I can access a piece of memory, I can read it again, and I can work out the difference. And based upon that amount of time and some calibration, I can work out, is that memory access, is that thing I'm accessing in the middle, was that in the caches or not? And as I said, a lot of architectures provide instructions that let you do this. You don't need an instruction. There are other ways to count time. And some architectures provide a way to guarantee you flushed something from the cache. That gets very useful a bit later on. But there are other ways to do that. You can look up displacement flushing if you're interested. And as I said, you might even be able to optimize it with some of these other variants as well to see if data is in caches. Well, why is that useful? Let's think about that. We'll come back to it. I'm going to skip prefetching. Okay, now we're going to talk about branch prediction. It'll all come together in a minute. This is a complicated topic, guys. You know, you're getting a deep dive here, right? Let's talk about branch prediction. So when I'm running code on a machine, I may hit points in my execution where I'm trying to decide, is my program going to go one way or another? If this, do that, or do that instead, right? Now, when I hit a branch in my program, I'm going to test, for example, if it's raining, do this thing. Well, I may not actually have the value of raining available to me at that moment for a couple of reasons. It might be in slower memory. I need to pull into my caches. That might take a bit of time. Or it might be some calculation I have to perform. And for those reasons, there can be cases where I hit a branch in my code to go one way or another, and I don't instantaneously know which way it's going to go. So I can stall my machine and wait, or I can continue running. I can guess which way my branch is going to go. And I can build on this, build on my out-of-order machine. I can build this concept of speculative execution. What I can do is I can say, I have this condition here. If R1 is 0, do this other stuff. I don't yet know the value because I'm loading it. I'm waiting for it to load. So what I'm going to do is I'm going to go into a special mode of execution called speculation. And I'm going to keep running these instructions. I'm going to guess it's going to go this way. I don't know that. So I'm going to tag each instruction and say that it's speculative. Right? If later on I discover which way that branch is supposed to go, and I'm wrong, I will flush everything that's purple here. I will forget about it. And because I've tagged it specially, I've not retired it, I've only kept its interim state, the idea is that you're never aware that I did this. It's an optimization. If I'm right, the machine keeps going, it's a bit faster. If I'm wrong, I have to throw away some state, but I'm no slower than if I just waited to find out the result of that conditional check. So speculation is something that we build in out-of-order machines. It's part of our branch prediction hardware, and we use it to get a performance optimization. When we're speculating, if we have any erroneous conditions in our program, what we will do is we will also tag them here. Right? So if I try to perform an illegal instruction or do something that's not permitted, I won't actually take an error, take a trap. I won't do anything about it because I don't know if this is actually supposed to run. I'll just mark it, and later on, if I decide that that was supposed to run, then I'll handle that later. So, as I said, if I'm correct when I hit a branch, it's called resolving a branch. If I'm correct, then I continue, and everyone just gets a speed up. If I'm wrong, I have to do some housekeeping. But the idea is that you can never observe that machine. You can't observe the fact that I did this speculation. It's supposed to be visible to you. I can talk a bit more about conditional and indirect branches, but I think I will just skip to how branch predictors work a little bit. So if I have two different applications running on my machine, how does the branch predictor actually work? Well, what it does is it has a data structure in memory, and it will look at the actual memory address of a potential branch instruction, and it will, in different ways, because implementations vary, record the history of that branch. So the last 10 times I saw this branch, I went that way. Probably means the next time I'm going to go that way as well. And in fact, in some hardware, I even have fancy stuff like loop predictors. They can work out not only, is this branch probably going to go that way, but I even know it's a loop. I can just magically work that out using some complicated hardware. But there may be many different components to my branch prediction, and fundamentally they will use some structure that tags the history of branches. And I want you to think about the fact that this tagging that I do it could be expensive. I could need a lot of memory if I were to try to store the address of every branch my program ever took. So instead, what I do is I optimize this structure, and I may only use a little bit of the address for that branch. So consequently, I could have two different programs with two different branches, and my branch prediction hardware may not be able to tell those apart. Okay? And then I have a variant of those conditional branches I talked about called indirect branches. That's when I have what you would call a virtual method or some kind of function pointer. I don't know where I'm going to go to. I also have hardware that, a bit like what I described before, can guess indirect branches in my programs. I'm going to skip through the optimization. All right, now I'm going to talk about these particular attacks because that took a bit of time. Okay, so you learned a lot. That was a whole semester's worth of various computer science stuff. I'm glad you're still awake. Let's talk about these two vulnerabilities and how they layer upon that. So, these are branded vulnerabilities. They were discovered by both academic researchers and also by Google Project Zero. And because they were discovered by researchers, I love the researchers, but you have to give it a cute name, right? So, Meltdown and Spectre it is, because variants 1, 2, and 3 don't really sound sexy, do they? Now, by the way, we were actually tracking these guys for a while, and I knew that this was the research team working on the project. And of course, there are websites you can go to where you can track everybody's domain registration. So I was using a side channel for some time to monitor the researchers to see what they would name it. So we discovered the Meltdown and Spectre domains the moment they registered them in December, and consequently had a little bit of time to figure out how they would position it. And what these attacks do is they exploit the things I just described to you to bypass normal system security boundaries. And let's go through how they do that. Well, firstly, if you're on a Linux machine, don't panic. Don't let your machine panic, because very recent Linux kernels, and certainly those from the distros, will very soon start to have this directory, sysdevices, system CPU vulnerabilities. We are thinking there may be more over time. It's good to leave room, right? And you will see entries in there for these attacks and then potentially future ones, along with what your machine is doing to mitigate this, right? That's not to fix it, because fixing it would require that we change the hardware in some cases, but we can mitigate it. We can take a performance hit and do something to remove the ability to exploit these attacks. So Meltdown relies upon some implementations of speculative execution literally following what Tomasulo did. And the key piece is that they handle exceptions, they handle problems from accessing data you're not supposed to right at the end. They allow you to speculatively do something, but then they say, before I retire, before I ever complete that operation, I'll just make sure I'm supposed to, and I'll throw it away if I'm not. So you might see a piece of code like this. Don't worry, we'll talk through what it does in a moment. In fact, I think I have it on the next slide. Okay, so I might have some secret data. Who knows what it contains? It's some magic data in my Linux kernel I want to read. And if I can arrange for a little piece of code to run speculatively, that means it's not actually necessarily going to be part of my program. I put it inside a branch that may or may not run. What I can do inside that piece of code is I can read that pointer quite happily. Now, if my program ever retires those instructions, I'm going to get an exception and it's going to crash. That's not useful, right? But what I can do, while the speculation is happening, I can use the value of that data to access some other data that I do have control over. And I can actually influence which data I access. Remember I said before, I can also determine whether something is in my cache based upon the access time for it. So I've got all the pieces I need. I figure out the data I want. I mask out a little piece I want to read. I then access some other piece of data I have control over, and the offset I access is based upon the value I just read. And then what I'm going to do, back outside of my speculation, is I'm going to measure which of those two locations I loaded. If I load one location, for example, 100, that means one thing. If I load, if my code loaded from the other location, that means something different. The actual value I read isn't visible to me, right? The speculation hardware took care of throwing all that state away. But because there's a shared cache, and I can observe what happened from the point of view of the cache, I can see that value, and I can therefore consequently use the same piece of code I gave you before to work out which of those locations, that 0-1 signaling, I can reconstruct that piece of data. I can do that in a loop, and I can read out the data. Now, the actual Meltdown exploit you'll read online is a bit more detailed, and they've got some optimizations. This is the version that I put together in December, because we had to mitigate this, and we weren't given reproducers, just enough to be dangerous, and then some folks, I think I was told that we were not that sophisticated, so don't worry. Well, I don't like being told that, so I went and figured it out and made a reproducer. That really annoys me when someone says that, so that was great. So this is what my code does. The actual code the researchers published is a little bit more optimized, but you get the idea. You can't read that secret data, but you can observe what it was based upon what it did to the caches. And here's the example code. And you can read through the slides to kind of get that to make a bit more sense for you as well. So when the right conditions exist, I can exploit this. How can I mitigate for it? Well, there are certain circumstances required to make this possible to abuse. For example, in some implementations, it might have to be in my very innermost level 1 cache. I might be able to flush that cache whenever I leave the kernel. There might be some people out there that are mitigating that way. The other thing I could do is I could change how I do my page tables so that the kernel memory is never visible when I'm running an application. I can do that. It's just a performance hit, because now every time I go into my kernel, I have to twiddle my page tables around. That's a technical term. And I take a hit. That costs me time, right? That's why Meltdown mitigation with page table isolation has a performance hit. There are optimizations. There's something called ACIDs. You can read more about this. Okay, let's do Spectre. I'm running low on time. Spectre. So we have this concept of gadgets. Gadgets, if you read about return-oriented programming, ROPs, these are common kind of stack-smashing attacks in security arenas. Gadgets are pieces of code that already exist in a victim or target program, and I'm going to cause that code to execute. It's already there. I'm just going to influence the environment so that that piece of particular code I found that does something I want, a similar sequence to what you saw before, load some data, I can infer what the data was based on the address it loaded, that kind of thing. I find a piece of code that's particularly interesting and I abuse it. So here's an example, Spectre variant 1. I might have a piece of code that reads some data in from the user, untrusted data. I might then do some other stuff. And it turns out some microprocessors will keep executing before they know whether they should. And so if I find a place where a particular bad sequence of code exists, I can exploit that. That's Spectre variant 1. It's difficult to do because I've got to find just the right code. It's got to be kind of on an entry point into the kernel. There's one reproducer. It's a bit messy. Let's talk. Oh, and the mitigation for variant 1 is, well, don't do it. So what I do is I shove an instruction in here that prevents the code from continuing past the point of doing potentially a speculative load. And that requires that I rebuild my operating system, my kernel. I talked about branch predictors before, so I've also got a variant 2 of Spectre, which is the branch predictor poisoning. And that is, since I know how branch predictors behave, there may be not fully disambiguated addressing. I can exploit that. I can have one process running that's training my branch predictor to guess wrongly when something else is running. If that something else is more privileged, or the kernel, I can exploit what will happen there. So I can poison my branch predictor, in particular my indirect predictor, to guess that it's going to make a jump into some code that it in fact is not. It will then speculatively execute whatever gadget code I want. So now I've got control over where that gadget code is. That's much more interesting to me, because in a very large thing like the kernel, I'm probably going to find a particular instruction sequence that's interesting to me. I set up the environment, I train my predictor, and I can exploit it. I'll wrap quickly. Mitigating it, there are two ways. I've got a big hammer, which is expensive. I can turn off my predictors when I go into or out of my kernel. Or I can use a technique that Google came up with called retpolines, which you can read more about in here, which change indirect calls into fake return calls. It's kind of interesting. It's like, if it hurts doing this, don't do it, right? So they have a way, particular code sequence, where they will modify what look like indirect function calls and make them look like function returns. So they won't use the indirect predictor. It's a cute hack. It's not nonsense. It's very interesting. And it does, unfortunately, also require you change your compiler and rebuild lots of things. So we are switching to that one because it's much more performant than turning off our branch predictors everywhere. And it also does cute stuff like put a harmless infinite loop in. If you're going to speculate, just speculate that and go away. It's kind of fun. Okay. And there are other variants of this coming. I'm going to wrap now. So related research. So this is just the beginning, right? Architecture junkies like me, I'm not going to say we're excited because that's a bit unfair. This is obviously very serious. And you should update your machines straight away and all that kind of stuff. But it is interesting that a lot more people are paying attention to these classes of attack now. And that means that researchers will find more of them. Hopefully we will make better machines as a result. And other related research will happen, right? So you guys can read about these later. You can read about the row hammer attack. And you can read about magic, which is my favorite one. That one is writing special sequences of instructions, which when you execute them, will physically age your hardware. Right? The bottom line is, everything you thought may or may not be possible. Now is a good time to go back and think about it again. Right? In summary, we talked about a lot of things. And you guys can go on Twitter, @Jon Masters, and you can find the links to all the slides. I will happily take, if there's time for one or two questions now, otherwise I will be around after, and I'd like to thank you very much.
We have time for questions, so please put your hand up and we can bring the mic to you.
While you leave, please be quiet. Stop talking. You can talk outside, but here, please keep quiet. Thank you.
Thank you very much. I'm here. So, how can two different research teams find the same flaws at the same time? What do you think about this? And I think it goes also with what you said in the end. Why were the previous flaws not so, talked about?
Yeah. Good question.
Just a second. This part about keeping quiet while you're leaving.
Yeah, if you're leaving,
can you please just shut up? Thank you.
Thank you. Usually people tell me to shut up, but this is better. I like this. The question is, how did several teams find this at the same time, right? Well, it's very interesting, actually, that most of the teams were in Austria, Germany kind of area, and all the guys knew each other. I'm sure that had nothing to do with it. But I think more specifically, if you look over the last few years, the guys at the Technical University of Graz, who are absolutely amazing, they found a whole sequence of different related exploits. So this is built over time based on previous research. So the time was ripe for this to happen. And then one of the guys posted a blog last July that came very close to the Meltdown attacks. The first thing we did when we were mitigating is discover all their research and go back and read all this stuff. And that was very helpful. So, probably anyone else who was doing research in the interim and paying close attention probably would have seen that, and that would have helped. So it was just coincidence. That does happen based on lots of other research that it was all happening over time that just came together. Another question?
I'd like to say again that both Meltdown and Spectre from scratch in 54 minutes is pretty impressive. So well done.
Thank you.
Do you think that this means that we need to be designing processes which are easier to change the way they work after the fact? Or do you think that adding that capability would have other negative consequences, such as the ability for rootkits and so on, that would actually outweigh the benefits of being able to perhaps tweak them more in the field?
Very good question. So firstly, I didn't get time to go into it, but on slide 80, there were 90 of these. On slide 80, I have one on how microcode, millicode, and chicken bits work in processors, and how you can basically update some of them after the fact, or use these things called chicken bits. Every processor that's built these days, especially the really expensive ones, the x86 ones will have up to 10,000 little knobs called chicken bits, so you can chicken out. And you can say, this little piece of the design, I'm not sure it's going to work, so I might just make it possible to turn it off later. And so you have about 10,000 different variants of that in most of the high-end chips. I'm not joking. And you can normally find a combination of those. You can turn something off. Microcode's a little bit different. You can read about, I've got a whole explainer on that. I do think we have to build chips that are easier to update. I don't think the answer is just, let's build RISC-V machines everywhere. There's nothing here that separates any of the commercial chips from anyone else's design. It's just everyone building processors should think about designing for in-field mitigation and in-field updates, design for security, and also consider this. If you are targeting a new market now, I'm very fond of ARM servers, some people know this. I always tell the ARM guys, if you want to be successful, you're going to go after public cloud. So that's now like 100 million, 10 million machines, all homogeneous and all an attack target. So you better design those kind of processors so they can be very easily fixed. So I do think there's a lot we can learn. I think the industry is learning a lot, but there's more to be done. Another question. Yep.
Should we be afraid of illegal instructions that may appear in memory, and what happens if they are speculatively executed?
Illegal instructions. What happens if we speculate those? It'll vary in the implementation, but usually it'll just tag it and say, it'll probably before it hits decode. So in the front end of the machine, it'll see it and say, I'm not even going to send that because I know that's not a valid instruction. But if you had an instruction like, the example I would use is divide by 0, right? That's a more classic case. I'm going to tag that I'm doing a divide by 0. I'm not going to actually send an exception to the program because I don't know if I'm actually going to do that. But actual legal instructions, I probably hit it earlier in my decoder. I say, yeah, I don't care about that.
You got one more?
One more?
Yes, up here. Thank you. So it's a bit of a political question. Up here.
Where?
Yeah. Do you think this could have been prevented? As in, the architects who designed those things kind of knew about it, but they were also saying, oh, we would accept the backlash, like this Dieselgate kind of thing?
So it's a good question. So I tend to be less in the conspiracy side of that, and I'm not saying you do. What I think is, those of us who studied branch predictors in school, and some of you probably did as well, right? You read about it at the time, you think, gee, I wonder if the context, no one says gee, but let's say I said that. The context from one state might still leak into another, and you sort of, in class, they'll say, well, never mind, after a little bit of time, those entries will just get displaced. And you say, oh yeah, sure, that makes perfect sense. And you don't think about it. And there are generations of students who've heard that and said, oh yeah, sure, no problem. And there are generations of students, by the way, who've also said, oh yeah, those extra indexing bits, I don't need a full set of bits, I'll shorten it. Again, so after this came out, I actually pinged a bunch of the sort of well-known academics and asked them to make sure that their classes have been updated, to make sure that they're not teaching anyone this now. But I think we've all learned the same things. Everyone who designs processors, they all went to the same schools, they all know each other, they build things the same way. They all think of the same kinds of things as not being possible or very unlikely. That's how this stuff came about. I do think we can learn a lot, and we can prioritize security, but again, while we are in a world where what will sell you a new laptop or a gaming device or anything else or a phone is something that is fast and cheap. While that remains the number one thing, designers will fall over themselves to get you that 20% more performance or whatever they can get you. So we also have to, as consumers, demand more in terms of security as well. Yep.
Okay, I'm very happy that I'm asking this question after this answer, because what you just said seems to me that you're saying we need different incentives to incentivize security. So my question is, should AMD, Intel, chip manufacturers be liable to some extent for what happened? Of course, nobody assumes malicious action on their part here, right? But if my screen stops working at some point, I'm getting a warranty replacement, right? I don't think everyone will get warranty replacements of their CPUs. Perhaps they should.
So, I think it's a good point. I think this is me. That's your question over there. This is a 10-foot pole. And this is me conveniently dodging it. But I do think you raise a good point, and I hope people discuss it. While I'm wearing this shirt, I'd rather not take a position on that. But thank you for asking it. And let's debate that, right? Okay, is it time for any more? Okay, thank you.